Welcome to CS 4700 or 5700 if you are taking this as a graduate student. This course is an introduction to the theory of computation, and we will examine three distinct topics over the course of the semester: automata, computability, and complexity. So let's take a moment and briefly summarize each of these. What we are really striving for is to gain an appreciation for the fundamental capabilities and limitations of computers. Automata explores what it means to compute something at a very fundamental level. We need to develop a model of computation before it makes sense to even consider whether or not it is possible to compute something in particular. Once we have a useful model of computation, we can begin to explore what kinds of problems can and cannot be computed. But even if we can show that a particular problem is solvable in theory, it may not be solvable in practice. Computability is only concerned with whether or not a problem is solvable given infinite resources such as time, memory, energy, or whatever other resource might be involved. But in the real world, these resources are finite and limited. This is where the notion of complexity comes into play. Consider the problem of sorting a list of objects, something that all of you have probably written programs to do. It's not surprising that using a given sorting algorithm, it takes longer to sort 1,000 items than it takes to sort 100 items. But how much longer? Does the amount of time double if we double the size of the list? Or does it quadruple, or what? Being able to get a handle on the complexity of a problem is extremely important in the real world. Some problems that are of immense practical importance, for instance, routing packages or planes around the world, is a problem that turns out to be immensely complex. So much so that we have to find ways of narrowing the scope of the problem to something that we can solve in a reasonable amount of time, even though it means that the solution arrived at is almost certainly far from the optimal solution that could be obtained if we had the resources to solve the full problem. But just knowing that the problem is too complex to solve in practice is not only enough to prevent us from wasting a bunch of resources trying, it can also give us insight into why it is so complex and how much we are likely to have to constrain our simpler version before we have something that is practical to solve. For a somewhat better view of our motivation for what we are going to study, let's look at these three topics in reverse order, starting with complexity, since this is usually what we really want to get a handle on when all is said and done. We might have a problem that, in theory, we can solve, but that in practice we can't. Complexity looks at the resources that are needed in order to perform a computation and how they scale with the size of the problem. In this course, we're going to focus on only the time complexity because that's sufficient to get the concepts across. We'll want to get a feel for how the time needed to solve a problem scales as the size of the problems grow. Let's briefly consider the traveling salesman problem, which is generally described as a salesman that must leave his home city and visit a list of in cities before returning home. The first part of the problem involves determining whether there even exists a route by which the salesman can visit all of the cities exactly once, starting and ending in his home city. The second part is to determine the optimal route in terms of total distance traveled. One way to solve this problem is to enumerate every conceivable order in which the cities could be visited, and then checking each one to see if the actual connectivity between the cities permits that route, and keeping a record of the shortest route seen thus far, updating it as shorter routes are discovered. We've just established that this problem is computable. We have a simple, in fact downright trivial, algorithm to compute it. But here's where complexity comes into play. The number of ways to order in cities is infactorial. If there are 5 cities to visit, there are 120 possible orderings to evaluate, which doesn't sound too bad. But if we double that to just 10 cities, the number of possible orderings is over 3.6 million. If there are 20 cities, that grows to over 2 billion ways to do it. If we had a computer that could evaluate 1 billion of those orderings a second, it would take 77 years to evaluate them all. There's no point even talking about the case where our salesman is tasked with visiting each state capital in the continental United States. So we can safely conclude that this algorithm, brute force enumeration, is a non-starter for actually solving this or any comparable problem except for the smallest of problem sizes. But does that mean that there isn't a different algorithm that is much faster? And if there is, what does its time complexity look like? Here is a very important point. We must distinguish between the complexity of a problem and the complexity of any particular algorithm that solves that problem. Once again, consider the familiar problem of sorting a list of objects and imagine that it is a brand new problem that has never been solved before. Someone finally tackles it and comes up with a solution, such as bubble sort or insertion sort, that runs in n squared time, meaning that for sufficiently large versions of the problem, doubling the size of the problem results in roughly a quadrupling of the time to solve it. If this were the only known algorithm to solve the problem, we would tend to claim that the problem itself is of n squared complexity. But that's not really the claim we can make. What we are really justified in claiming is that this problem is of no worse than n squared complexity. Next week, someone might devise a much better algorithm, such as merge sort or quicksort, that can do it in n log n time. The complexity of our original algorithm hasn't changed. It's still n squared. But now we can assert that the complexity of the problem is at worst n log n. At any given time, the complexity of a problem, not an algorithm, is no worse than the complexity of the best known algorithm that solves that problem. But before we can start talking about the complexity of the algorithm that solves a problem, we need to be able to determine whether a problem itself is solvable. This is the realm of computability. We don't care about whether a problem is solvable in a practical sense. We'll deal with that down the road when we examine its complexity. What we care about is whether it can be solved at all, given unlimited computing resources such as time and memory. Here it is important to distinguish between solving a general problem and solving a particular instance of that problem. For example, we might have a particular computer program that takes some input, does some processing, and then produces some output. That particular program might be very simple and written in such a way that we can examine it and determine that no matter what input is given, it will always complete its task and exit properly. However, this says nothing about whether the general problem, namely whether an arbitrary program will function as specified, is solvable. A problem is considered to be solvable, decidable is the term that we'll be using, only if it is possible to solve every possible instance of that problem. In this case, the general question of whether arbitrary programs will always halt, regardless of what input is given, turns out to be undecidable. We can and will prove this mathematically. The implications of this are rather profound and quite useful. Once we have proven that a particular problem is undecidable, it is no longer a matter of putting in enough time, effort, and money to discover or devise an algorithm to solve it, at least in the general case. We've proven that no such algorithm can exist. In this case, this essentially means that all of the software that impacts our daily lives, be it financial institutions or the programs that control the jet engines on the plane we are on, can't be guaranteed to actually work correctly. But knowing this, we can look for ways to narrow the scope of the problem to something that can be solved. In this example, this is a field sometimes referred to as provable programming. The goal isn't to prove that an arbitrary program meets its specifications, but rather to restrict how we write programs so that the results fall in a smaller subset of all possible programs for which we can prove their correctness. A question that immediately comes to mind, assuming we are successful at achieving this, is whether we can devise a set of programming guidelines that would let us write a provably correct program for an arbitrary but solvable problem. Without doing any further research or analysis, we know the answer, because we know that if we could do this, then the general problem we started with would no longer be undecidable, and we've proven that it is. Finally, before we can start talking about the complexity of a problem, we have to understand what it means to compute something, which brings us to automata. We solve problems using machines, what we generally refer to as computers, and we are going to look at three distinct categories of machines. These are really computational models, and we need very simple models in order to be able to analyze whether or not they can solve certain problems. First, we're going to look at what are known as finite automatons. In fact, we're going to devote roughly a third of the course to these very simple machines. A major reason for this is that we will use them to establish a firm foundation that will be relied upon heavily throughout the rest of the course. Finite automatons are simple state machines that have no memory beyond what state they are currently in. Each time they receive an input, they move to a new state based solely on that input and their current state. These machines, although extremely simple, have profound and wide-ranging practical application. Many electronic systems are based on nothing more than finite state machines. Also, nearly all compiler and interpreters use a finite automaton to identify the program's tokens, which are essentially the words that make up the program. For these reasons alone, studying finite automata has significant value. Once we've wrung everything we can out of finite automatons, we're going to add a bit of complexity to them by adding a stack data structure. Most of you worked with stacks before, so there's nothing here that's going to be terribly unfamiliar. The result is known as a push-down automaton, and we will discover that doing this substantially increases the kinds of problems that we can solve with these machines, and that there are still plenty that we can't. From an everyday practical standpoint, above and beyond the value of push-down automatons to the theory of computation, these machines are the backbone of compilers. They take the tokens that were identified using a finite automaton and break the program down into its logical structure from which we then generate executable code. Finally, we are going to take our push-down automaton and replace that stack with a tape data structure. Making this seemingly minor change will result in a Turing machine, which is the most powerful model of computation that we yet know of. In fact, anything that can be computed by a Turing machine. Now, having said that, this claim is actually a bit circular, since we declare a problem to be computable if and only if it can be computed by a Turing machine. But while this seems rather unsatisfactory, people have spent their careers trying to identify problems that can be solved in some meaningful way, but that can't be solved by a Turing machine. Even now, as the age of quantum computing dawns, we have been unable to find one. This doesn't mean that someday someone won't, but if it happens, it will merely give us yet another model of computation and further extend our understanding of computability and invariably complexity.